I am going to explain file allocation methods, which is an important concept in operating systems. File allocation refers to the way an operating system stores files on secondary storage devices like hard disk and SSD. This method, used to store files, has a direct impact on system performance, storage efficiency, and reliability. In this presentation, I will discuss the three main file allocation methods: contiguous allocation, linked allocation, and indexed allocation. I will explain how each method works along with its advantages and disadvantages. Finally, we will see why modern operating systems combine these methods instead of relying on just one. So let's begin by understanding the basic storage challenge. Before we learn about the allocation methods, let's first understand the storage challenge. Whenever we save a file, it is divided into small units called disk blocks, which are stored on secondary storage. The operating system must keep track of these blocks and map them correctly to the file. While doing this, it tries to achieve three main goals. First, it should provide fast access so user can use and open files quickly. Second, it should reduce fragmentation, which helps use storage space efficiently. Third, it should support easy file growth, allowing files to increase in size without moving all the existing data. Since achieving all these goals together is difficult, different file allocation methods were developed. Now let's talk about the first method, which is contiguous allocation. In this method, all the blocks of a file are stored together in one contiguous sequence on the disk. The operating system only needs to store the starting block and the file length, making this method very simple. One major advantage is that sequential access is very fast because the storage is stored continuously. Random access is also efficient since the required block can be calculated directly using its position. However, this method has some drawbacks. It causes external fragmentation, making it difficult to find large continuous free spaces. Also, if a file needs to grow later, extending it becomes difficult because the next block may already be occupied. Although contiguous allocation performs very well initially, it becomes less efficient over time. As files are created and deleted, the free space on the disk gets divided into many small gaps. This problem is external fragmentation. Even if there is enough total free space, it may not be available in one continuous block. So storing a large file becomes difficult. One solution is disk compaction or defragmentation, which rearranges files to create larger free space, but this process takes time and interrupts normal system operations. Another issue is reserving extra space for future file growth. If that reserved space is never used, valuable storage gets wasted. That's why contiguous allocation isn't ideal for frequently changing systems. To solve the fragmentation problem, linked allocation was introduced. In this method, file blocks can be stored anywhere on the disk. Instead of being placed together, each block contains a pointer that tells the operating system where the next block is located. The operating system only stores the address of the first block, and the remaining blocks are connected through these pointers. The biggest advantage is that there is no external fragmentation. Because any free blocks can be used, files can also grow easily without moving existing data. However, every block needs to store a pointer, which slightly reduces the availability storage space, and accessing data randomly becomes slower because the system must follow the chain block by block. Although linked allocation removes fragmentation, it also has some disadvantages. The biggest drawback is slow random access. If we want to access a particular block, the operating system cannot jump directly to it. Instead, it has to start from the first block and follow each pointer until it reaches the required block. This makes random access slower than contiguous allocation. Another issue is that every block stores a pointer, which reduces the amount of space available for actual file data. Also, if one pointer gets damaged or corrupted, the remaining part of the file may become inaccessible. So, linked allocation works well for sequential access, but it is not suitable when fast random access is required. An improved version of linked allocation is called the file allocation table or FAT. Instead of storing pointers inside every data block, FAT keeps all the pointers together in a separate table. This allows the data blocks to store only actual file data, making storage more efficient. FAT also makes file management and recovery easier because the operating system only needs to examine the allocation table. This method became very popular in early version of Windows and MS-DOS. However, FAT also has some limitations. Since all allocation information is stored in one table, it becomes a single point of failure. If the table gets corrupted, many files may become inaccessible. Large storage devices also require larger FAT tables, which can affect performance. Now let's move to indexed allocation, which is widely used in modern operating systems. In this method, every file has a separate index block that stores the addresses of all its data blocks. Whenever the operating system needs a particular block, it simply checks the index block and directly accesses the required location. This provides fast random access while also avoiding external fragmentation because blocks can be stored anywhere on the disk. This method is highly flexible and works well for both small and large files. However, index however However, index blocks also occupy some storage space, and managing them adds a little complexity. Even with this overhead, indexed allocation offers an excellent balance between speed, flexibility, and efficiency. As storage devices become larger, indexed allocation was further improved. For small files, a single level index is enough, but for larger file, operating systems use multi-level indexing, where one index points to another index. Another technique is indirect blocks, which increase the addressing capacity without requiring an extremely large index table. Modern file systems also use extents, where a group of consecutive blocks is stored as a single entry instead of storing each block separately. This reduces metadata overhead while maintaining good performance. These improvements allow indexed allocation to efficiently support today's large storage devices and high capacity file systems without sacrificing speed or flexibility. To conclude, we have learned that each file allocation method has its own advantages and disadvantages. Contiguous allocation provides excellent speed but suffers from external fragmentation. Linked allocation removes fragmentation and allows files to grow easily, but random access becomes slower because blocks must be accessed one by one. Indexed allocation combines the advantages of both by providing fast, direct access while avoiding fragmentation, making it the most suitable choice for modern operating system. In practice, today's file system use hybrid techniques such as extents, allocation maps, and journaling to improve performance and reliability. So the best allocation method always depends on the type of workload, storage requirements, and expected file growth. Thank you. That's all from my side. I'm happy to answer any question if you can ask on the comment section.